Welcome back to this explainer from the Foundry by Forge College. I am so incredibly pumped you're here today. We're picking up right where we left off, after exploring the role and importance of turbine in Solana data transfer, and today, well, we are unrolling the blueprints. Literally. Notice our dark green and orange ink sketches floating on this beige patent paper here? We are unpacking an absolute masterclass, the principles of data sharding. So let's just jump right in with a fundamental problem. How on earth do you send a massive file across a super high throughput network like Solana in literally milliseconds? Well, think of it this way. You cannot, absolutely cannot, ship a giant sprawling mansion across the country on a single flatbed truck, right? The logistics would be an absolute nightmare, and the network bottleneck would bring the whole thing to a grinding halt. You have to break that mansion apart into transportable pieces, pack them on multiple trucks, and flawlessly rebuild the whole shebang on the other side. And that is exactly why Turbine uses data sharding to keep the network absolutely flying. All right, so here is our technical blueprint for today. We'll kick off with a quick intro to data sharding, then we'll define keys and boundary rules. After that, we'll look at choosing a fragmentation pattern, cover mapping, routing, and transfer, check out reassembly and erasure coding, and finally, we'll calculate the ultimate scalability payoff. Okay, Section 1, Intro to Data Sharding. This is really the fundamental logistics of Solana data. So what is data sharding? Well, it's the deliberate division of a large data set into disjoint segments, which we call shards, that can be processed, stored, or transferred independently, in parallel. Instead of trying to force an entire data set down a wire as one massive heavy atomic object, sharding lets us send multiple data trucks down completely different network highways at the exact same time. It's really the ultimate divide and conquer strategy for data. Moving right along to Section 2, Keys and Boundary Rules, or as I like to call it, defining the what of our shards. Okay, so these two primary elements, they act as the absolute, non-negotiable engineering laws for our data. A shard is mechanically defined by two things: a shard key, which determines membership, and a boundary rule, which is the concrete rule you apply to that key. So for example, maybe a rule is every 4 megabyte contiguous slice. Pretty straightforward. Together, this key and boundary form an explicit, ironclad contract between the sender and receiver. There is zero guesswork here, guys. It fully describes exactly how the shards are created and exactly how they must be reassembled later. Next up, Section 3, Choosing a Fragmentation Pattern. This is all about strategic packing for the data journey. So while the boundaries we just discussed dictate the what, the fragmentation pattern is the how. It's the specific method used to actually execute the split. And honestly, this completely determines the observable behavior of the transfer as it's zipping across the network. Now, we've got two canonical choices here. On the left, we have contiguous fragmentation. This essentially slices the payload into sequential byte ranges. You're keeping the data sequential, kind of like packing one whole room of that mansion at a time. Then on the right, we have interleaved, or striped fragmentation. This method distributes blocks in a round-robin fashion. So instead of keeping things sequential, you're dealing the data out across your paths exactly like you deal a deck of cards. And the crucial point here is really understanding the trade-off. Contiguous fragmentation is fantastic if you just want, say, one room of the mansion. It heavily favors simple reassembly and partial range reads. But if a single truck hits traffic, boom, that whole sequential chunk is delayed. Interleaved fragmentation, on the other hand, absolutely maximizes your parallel throughput. Because you dealt the data out like cards, if one truck hits a bottleneck, the whole builds doesn't stall, you're still receiving parts of every logical range. The only minor catch is, well, you do need a bit more metadata to piece it all back together. All right, Section 4, Mapping, Routing, and Transfer. Let's look at the step-by-step logistics workflow. Okay, here is the 6-step logistics process laid out. Step 1, we select the key and boundary. Step 2, we fragment the payload and add the metadata. And I gotta say, missing the metadata in Step 2 is literally like shipping 1,000 identical unmarked boxes across the country without any shipping labels. An absolute nightmare for whoever is receiving it. Anyway, Step 3, we map those shards to transfer channels. Step 4, we communicate the routing. Step 5 is the parallel transfer. And finally, Step 6 is reassembly and verification at the destination. Now, I really want to zoom in on a massive speed hack used during that routing phase, deterministic mapping. Instead of sending a separate index to tell the receiver which shard goes where, you just use a shared mathematical rule, like a hash function. Because both sides already know the rule going in, you can bind shards to channels without ever needing a communication round trip. Skipping that back and forth handshake, Yes, that saves incredibly precious milliseconds. Almost there. Section 5, reassembly and erasure coding, rebuilding the mansion flawlessly. Think about this highly relatable scenario. What happens to a 99% complete download when one single packet fails to arrive? Normally, you'd suffer the painful latency of asking the sender to reship that missing piece, right? Well, instead, we use a brilliant forward error correction method called erasure coding. During fragmentation, we actually add extra parity shards. This means if one data truck crashes off the highway, we don't have to call the sender to ship a new brick. Instead, the receiver uses lightweight math, stuff like Reed-Solomon equations, to instantly manifest a replacement brick right on site. It's like magic. You trade a tiny bit of CPU power to completely eliminate the need for retransmission. Finally, Section 6, the scalability payoff. Why all of this actually matters for high-throughput networks. The most crucial point of this whole explainer is this multiplier right here, n. By sending n shards across n independent paths, you reduce the transfer time by nearly a factor of n. It is the ultimate scalability payoff, guys. You aren't just sending data, you are fundamentally multiplying your network's capacity. But to achieve that massive payoff, you actually have to measure the real-world overhead. You've got to evaluate per-path capacity and bandwidth, the probability of correlated network failures, expected packet loss rates, and of course, the CPU cost of that erasure coding we just talked about. And just a heads up, as you dive deeper into the advanced learning courses over at Forge College, you'll actually learn to use these exact metrics to predict real-world network latency rather than just, guessing. So I'll leave you with this provocative thought. Will a single slow packet crash your system, or will you engineer it to be truly unstoppable? Data sharding, when executed with the right fragmentation patterns, precise deterministic routing, and mathematical erasure coding, is exactly how you build the unstoppable. I really hope this blueprint helped demystify how networks move mountains of data in the blink of an eye. To master the rest of Web3 architecture, be sure to visit the educational resources at forge.college. Keep exploring, keep building, and I will see you next time.